Awesome, thank you. Yay. Hi, everyone. Today's talk is a bit general. It's on ultrasound used in non-destructive testing. So I'm Oksana Trushkevich. I'm an assistant professor in School of Engineering at the University of Warwick. And I'll be talking about three different topics today. About EMATs, electromagnetic acoustic transducers, about magnetostrictive transducers, and about a bit more exotic topic of liquid crystals and how we can use them to visualize ultrasound and how we can use that for various applications. Again, thinking about non-destructive testing and ultrasonics. Let me check that the clicker works. Excellent. So first, I'll talk a little bit about non-destructive testing and structural health monitoring. Why do we do that? And then we move on to how we do that. And that's when the talk of EMATs and magnetostrictive patch transducers comes in, because they are one of the types of transducers that can be used. And also the last part would be about visualizing ultrasound. The main idea around this whole thing, the overarching idea is about moving towards low-cost, simple inspection or monitoring, which can be automated and which can be delivered remotely. And let me explain why. Now, first of all, what is non-destructive testing? Well, it's key to ensuring safety. This would be in any industry, in transport, in energy, and in civil engineering. Well, what happened with these, so the images that I'm showing, this is Hatfield tragedy. That's because the rail broke. We had the technology to detect cracks in rails, but the rails were not inspected in a timely manner. And that was because it takes time to inspect. Normally, you need to shut down the rails. You need to walk along the line or run a slow-moving train along to check for defects. It's costly, you have downtime. We need techniques that can do it faster and without the shutdown. Then this wouldn't be a problem. The problem with rack, again, we didn't have techniques reliable enough, and it was too expensive to test regularly or more frequently. And in fact, 80% of testing inspection cost is sending people over, putting up scaffolding. Then also there are issues with retaining and recruiting workforce. Now, ultrasound is used a lot in inspections, and it's a great tool. I think that that's what motivating me to work with in the area that I'm working, and the overall aim is simplifying and making inspections automatic, low cost, and suitable for large areas. Now, let's delve into how inspections are done at the moment. This is one of the photos that I found on the internet from a company called TSP Environmental. They're offering inspections of storage vessels. And let's look how they do that. So we have two people with access requirements. They are clipped in. And if you zoom in, then we see that the person is applying ultrasound gel to the vessel, and then they're going to test it point by point. I don't know how long it will take them to inspect the whole surface, whether they will access all regions, because there would be supports around that vessel where the thing is more likely to rust, and whether they can actually cover it in a day, going point by point, I don't know. Okay, do we have any better methods? Yes, if you look, TWI, really advanced company, they have robotic inspection. They have robotic arms, really powerful machines. You still see water. Water is a couplant. They use standard transducers, piezo transducers. They can inspect really complex shapes. The only thing is you need to remove that component. You need to bring it over to the robot. And is it completely automated? Well, no, we still have an operator. Okay. Oh, this one looks better. That's from Edify Technologies. This is the crawler robot. It can inspect vessels in power plants. There is no couplant. Fantastic. Shall we look at the bigger picture? Right. Still far from being perfect. Still, we need an operator to run it. Still, we haven't removed that big cost of sending somebody over. Now, another company that I found does something much more close to autonomous inspection. They could send a robot in which moves autonomously, makes smart decisions, sends it to the operator, but it only carries cameras. But the operator can see a variety of different measurements. Don't ask me why that person is still wearing a hard hat. They could be sitting and sipping coffee in the office, and that probably will happen eventually. Now, obviously, at the moment, the robot can only carry cameras, but you can just put ultrasound sensors on it and start getting more data, start seeing things inside the structures. But you'll keep that type of inspection in mind for the last part of my talk, where I'll be talking about visualizing ultrasound, because this is already an existing technology that works with visualization and image processing. But for now, let's look a bit more in detail into how we can generate ultrasound, and keeping these goals in mind about going low cost, simple, suitable for robotic inspection, or suitable for permanent installment, and so that you just come and measure, or the sensors send you data. So you don't have to send out inspectors, and you don't need to waste that resource and time and have that cost. Sorry, that was the wrong button. But first of all, let's talk about what ultrasound testing is and which types of waves it's using. I do not know about the community present here, but if you work in marine acoustics or acoustics of the environment, you would probably be more used to longitudinal waves. The same goes for medical acoustics. In solid bodies, we can also have shear waves. You can have bulk shear waves. We can also have surface waves, and we can have guided waves. And today, I'll be mostly talking about guided waves, in particular shear guided waves, because they are good for inspecting really large areas. I'll just have a quick draw of what a guided wave might look like. This is a LAM guided wave, and if you have a plate, if it does something like that, that's your regular plate, and that's a guided wave in that plate. This is a symmetric guided wave mode. The interesting thing about guided waves is that they are dispersive, and you can play with that. And no talk about mentioning guided waves will be complete without a picture of dispersion curves. And I promise not to bring it up again, but for those of you who want to know, I'm mostly working in the area of non-dispersive SH0, somewhere here. These lines are lines of equal wavelength, and I'm using wavelengths around usually 22 millimeters, very large wavelengths, lower frequencies. This is frequency thickness here. This is phase or group velocity here at the bottom. So I'm mostly using SH0 wave, which is not dispersive, or SH1, which is dispersive and more sensitive to certain types of defects. Let's move on to the ways of how we generate ultrasound. So we've seen these inspection methods where we used couplants. It could be water, it could be gel. Now, that's not always suitable for all materials. It's not always suitable for all conditions. It doesn't work for high temperature. I mean, really high temperature. So we need non-contact methods, and we have them. That's acoustic EMATs, electromagnetic acoustic transducers. The benefits of non-contact methods is that they work through coatings. You don't need to strip the paint. They could work on a rough surface. They could slide above hot surfaces, and they won't damage the surface. They won't contaminate surface with the gel or water. Not all surfaces like water. Another thing we'll be talking about today is if we are to leave transducers in situ, they have to be low cost. They would be in contact with the structure, or they could be contact transducers. They have to be resilient. They have to be low cost, and they would be suitable for continuous monitoring. So EMATs. Again, a very quick explanation of what an EMAT is. For those of you who know what EMATs are, please bear with me. An EMAT is effectively, it's a coil of wire. This one is obviously it's a coil of wire like that, and we can see it in cross section. And that's our coil of wire. When we put it above a conductive sample here, then we generate a mirror current or eddy current. And that current inside a conductive sample in magnetic field will generate a force, Lorentz force. So that's your right-hand rule. We have current, magnetic field, and force. In that case, we will be generating shear waves. They're extremely versatile because you can generate a variety of different wave modes depending on how you orient your magnetic field and how you make your coils. The downside is that they're not as efficient as piezoelectric transducers, and they can be sensitive to liftoff. But they are suitable for high temperature inspection, and they are good for inspection of fast moving surfaces. And here is an example of EMATs being used for inspection of rails in one of our projects. Now we are thinking about robotic inspection, right? So we can take EMATs and put them on robots. The only problem with EMATs is they require magnets. Remember, we have a big magnet, and then we have a coil of wire, and I'm trying to get this off. This is a transducer with magnets. The smaller the magnets, the easier it is to drag things over. So we are working on making transducers smaller. Obviously, if you make something smaller, it may work at higher frequencies, but there is a price to pay in terms of efficiency. So our earlier work was focusing on making miniaturized EMATs and to generate surface acoustic waves for surface wave inspection, looking at surface breaking cracks. And we wanted to see really small cracks, about 1 to 3 millimeter in length. And you wouldn't see them using bigger transducers. If you have a really large surface area of transducer, you just won't see really small crack, even if you are scanning. And with our small transducers, we were able to map these cracks. And these are really, really small slots. They are 1.5 millimeter deep in a block. And that one is only 1 millimeter length of the crack. And this one is 3 millimeters. And you can see both really clearly. But this is scanning point by point, which can be a little bit slow. And if we want to move away from scanning point by point, then we have to move into guided waves. And the guided waves that we work with, I mentioned already, these are SH guided waves. And to make an SH, to generate SH waves, again, for EMAT, you'll need a periodic array of magnets. And that's quite a lot of magnets. And if you look at standard EMAT designs to generate SH guided waves, if you are to do inspection with a slightly larger wavelength, which will allow you to access the dispersive edge of SH1 mode, which would be brilliant if you want to inspect wall thinning in plates, then it's really big magnets that you need to use, and it's difficult to move them around if the material you're inspecting is magnetic, if it's ferritic steel. So you either need a really big robot to drag that thing. Even if you put that on wheels, it's still really difficult to move. Or you need to do something else, like what we've done with miniaturization. So we asked the question of, okay, can we make that smaller? First of all, let's see how the force is generated. This is the side view, and that's again how we generate the force. There is nothing here that tells us how many periods we need to go into this direction. Maybe we can get away with just half of these. Let's see. We tried that. That's actually one of the devices we made, and it worked. Only the drag force is now 7 times smaller. That's pretty good. Can we make it even smaller? Just with 2 magnets for detection. For generation, it probably won't be as effective. It does work, just not as effectively. What happens is they become more broadband. You're not prescribing a wavelength strongly. But yes, it worked with much smaller drag force. Just to prove that it does detect defects, the black trace is from a line where is no defect. So we are sending guided waves on from one side and detecting it on the other side of the plate. And if there is a defect in between, we will notice it. So no defect is the gray line, and the dark black line is with defect. We lose a bit of energy in one of the wave modes. We can reference the amplitude is in first wave mode, and we know there is a defect. And these sensors, so this is our generator and 2 detectors, can go on a robot. Brilliant. So now that we have robotic inspection done and dusted, we know we can deploy our sensors on a robot. What else can we do? Well, we can start thinking about condition monitoring, permanent installation of sensors, because you can't always send a robot. You sometimes want to know things on a daily basis, or maybe on a monthly basis, but you don't want to move around a lot and do the scans. Maybe you just want to inspect a particular line of sight, or have a network of installed sensors which send you information regularly, and you can build up a picture. Because then you don't have problems of, are we inspecting in the same location or not? So for that, a brilliant candidate is magnetostrictive patch transducers. The benefit they have over EMATs is that they're extremely efficient. They are relatively low cost, and they are suitable for being left in situ. You can actually machine them, make them small, make them flush with the surface, and the cost of them would be less than £100 per unit. So you can actually start thinking about leaving them permanently. They are particularly suitable for generation of SH guided waves, because you've seen the EMAT design. It's not complicated, but it could be easier, simpler. And the design of magnetostrictive patch transducer for designing the same thing, for generating the same type of wave, would be even simpler. But first, we need to talk about what magnetostriction is. The definition is you put something magnetostrictive into magnetic field, and it changes length or dimensions. It is a quantum mechanic effect, and it's all about magnetic moments not liking to be aligned in one direction. So when you start putting them into magnetic field, there is a repulsion as they rotate to be along with the magnetic field. This is macroscopically. You get strain in the lattice, but macroscopically, there is a domain structure, and things are moving macroscopically as well. The general result is that when you put something into magnetic field and oscillate the magnetic field, you can get a bit of actuation. You can have a bit of a change in shape. What is also interesting is that if you have a bias magnetic field and an oscillating magnetic field, and you operate in this region of the curve, and this is the standard curve of change in length or magnetostriction change versus magnetic field. So you'll have a much larger response. This is Joule effect, and the inverse of it is Villari effect. And for this one, you need to have static and dynamic magnetic fields parallel to each other. Now, there is another type of effect called Wiedemann effect. This is about twisting in helical magnetic field. Now, what is a helical magnetic field? That's confusing, isn't it? Basically, if you have a rod and you send current along it, you will have magnetic field around it. And now if you place that in magnetic field that's facing along, that's aligned along the rod, then you will effectively generate a helical field and the rod will twist if it's magnetostrictive. It works through Poisson's ratio effect, and the beauty of it is if you take a strip of magnetostrictive material, a magnetostrictive patch, then it will want to twist in magnetic field with bias magnetic field and dynamic magnetic field. And that's what we'll use to generate ultrasound and shear waves. Now, this is an experimental graph of the efficiency as a function of bias magnetic field for a fixed current that we pulse through the coil, so for the fixed dynamic magnetic field. The interesting bit is that this is just efficiency, but if you look at what happens with the signal peak, the force that's generated is fully described by the directions of the bias field and the dynamic field, so you can have very precise control over what force you're generating. That's really interesting. Now, why do we even want to look at this? There are commercial systems already. They're very expensive, but they use magnetically hard materials. So they use such patches, but they're very brittle, very effective, but they require still pre-magnetization, and yes, extremely expensive. So the question is, if you use magnetically soft materials, these are soft, they're not brittle, they don't break, I can cut them with scissors, they're cheap, and maybe not as effective. They require permanent magnetic field to operate there all the time. They don't work with pre-magnetization as well, but it can be cheap. And the good thing about this is that this works, well, the Curie temperature is 780 degrees, so it can work at high temperatures. A lot of work has been shown in the literature about using these in a variety of geometries. You can generate torsional waves, you can generate shear horizontal waves, you can generate lamp waves. So these are all guided waves. There's a great review of that. And they all seem to have quite complex geometries, but this, we are just going back to basics and using a really simple geometry, just a patch and a simple racetrack coil and a pair of magnets for bias field. This is really simple. So we are generating an SH wave this way. The only difference from EMATs now is, well, first of all, the fields are in different directions. And second is we need a couplant. So here we have a couplant. You need to attach it, either mechanically pressing down or having something sticky in between. It's not too much of a problem. It can become a bit of a problem at high temperature, but there are solutions for that. With regular application with room temperature, you can even use double sticky tape, and it works beautifully. And it works beautifully on rough surfaces, and I'll show you a bit later how that performs. But the general idea that we are twisting the patch because we have this field, which is dynamic field, moving this way, and we have a bias field, and the patch wants to twist, and thus generates shear waves. Now, let me show you just how effective this effect is. I'm comparing with EMATs. These are, so I took glass plate so that it's completely non-ferritic, has no influence on generation whatsoever, and I've put 2 copper patches, 2 EMATs. I had to turn down the power because for magnetostrictive patch transducer, it was completely overwhelmed. The amplifier couldn't cope, it was just saturated. So EMAT on copper, which is good conditions for generation through Lorentz force was the black trace. Now, interestingly, if you put EMATs on magnetostrictive patch, they work better. This shouldn't be the case, but we later explained why that was. And if you use EMAT generation, but detection using Wiedemann effect transducer, which is again patch, as I showed you, patch and the coil into magnets, you get this huge signal. It's 2 orders of magnitude enhancement. Now, I promised you to show this how it works on rough surfaces, and the approach for example, for permanently installing sensors and monitoring whether we get any corrosion under support. So here, this is the kind of surface that we get. This is a pipe. This is corrosion area. And this is one of the patches where the coils and magnets go. The strategy is we send, because we generate both ways, we use that to our advantage, and we send one wave to the detector over the region that we can see that's not likely to corrode, and the other wave through the region which might corrode, and we just compare these 2 signals. So the black trace is taken at detector 1. So it first gets the signal that this big peak, it's shear horizontal SH0 wave mode. It comes from here, hits that detector. That's our big peak. At the same time, into the other direction, we are sending the same type of wave, but because once it passes through corroded region, only a small amount of it reaches detector 2. And that carries on this way, and that carries on that way. That's the second peak. So we can detect corrosion on the supports, and we can install them permanently and just come and read the data when we need to. We can also send guided waves. These are torsional guided waves along pipes. Now, this is a really simple way of generating torsional waves. It's so simple to make. You just need a longer coil and a longer patch and wrap it around the pipe, and have 4 magnets for this pipe diameter. The amazing thing is that we've put a generator on the edge, we've put the detector in the middle, and this is like the first peak is the direct peak, and then we have reflections from the edges and bounces that we are seeing in the detector. The length of the pipe section was 1.5 meters. We still could see things going on after 15 bounces, and I drew these lines by the speed of propagation, but also the length of the pipe, so we know exactly where we are in terms of length. So we can go 20 meters or longer in one go if we need to with these waves, and such sensitive generation and detection. And the last bit on magnetostriction that I wanted to share with you is that magnetostrictive patch transducers are distinct from EMATs. They have different geometry. They rely on magnetic fields only, not on currents, while EMATs rely on currents and magnetic fields. They require the sample to be conductive. Magnetostrictive patch transducers can be put onto anything and work. But EMATs combined with magnetostrictive patches themselves, so if I put my EMAT onto my magnetostrictive patch, well, first of all, they stick because they're magnetic, but this system is an interesting one as well, because the performance is enhanced, and you've seen some of it already. But what you manage to get is EMATs are not liking when you move them away from the sample. You can probably get away with 5 millimeters liftoff when you lift your EMAT away from the sample you're trying to generate in, maybe 10, but not beyond that. When we placed a magnetostrictive patch onto the sample and lifted the whole EMAT, coils and magnets, above it, I've used a physics book. It's a thick physics book. Don't know whether you have it as well. University physics. It's 50 millimeters thick, and I've put it onto the patch, and then I've put transducer on top of that. So I have 50 millimeters lift off, and I was still detecting this signal. This is 16 averages. This is not 64 high averaging, 16 averages. But detection was done using also the Wiedemann effect, which was a bit more sensitive. So by using our sensitive detection and magnetostrictive patch to upgrade the response of an EMAT to liftoff, we were able to achieve that 50mm liftoff. So you can actually think of starting to place magnetostrictive coatings or patches permanently installed, and then come and inspect with an EMAT through thick insulation if you need to. Right. And now let's move on to other approaches to large area sensing and inspection, and that's ultrasound visualization. But first, let's have something to visualize. What shall we visualize? I promised you that we will be playing ultrasonic drum. This is what I usually call it. Technically, if you take an air-coupled transducer, flexural transducer, which is a parking sensor, for example, they operate at 40 kilohertz. They are just a cap of aluminum cap attached to a piezo element. And it behaves a little bit like, if you're familiar with plate vibration or any type of vibration, you will get these resonant modes where at fundamental mode, everything will go up and down. You can also have higher modes where you have these rings forming. So this is MATLAB model of a cap vibrating, and this has, I think, two nodal lines, so that would be 2-0 mode, or something similar. So imagine we have this cap, and we drive it at high frequencies so that it shows us an interesting pattern. Now, this is the system that we will be using to see whether we can visualize such motion, such displacement, ultrasound, or mechanical vibration, depending how you define that. So we use this, and of course we need to have a gold standard, and the gold standard for visualizing vibration and ultrasound is laser vibrometry, or also laser interferometry is another method. Laser vibrometry, we took a cap, we drove it at 740 kilohertz. This is 11-0 vibrational modes. It has 11 nodal lines if you really want to count them. There are 11, I promise you. The number of the rings, so each ring shows you amplitude going up or down. If you can see, the displacement goes from negative to positive. So it shows you the phase of the displacement. That map shows you the phase. If you look at just the edges of these, you can count the number of nodal lines. That's great. The only problem is that the system costs, even the cheaper one costs about 10K, and it takes about 8 hours for scanning. If you have a better system, more modern system, more expensive system, it will probably take you less time, but still it's a point-by-point scanning. And you probably can't afford checking every single vibrational mode if you, for example, are interested in that. So we're wondering whether we can make it faster, simpler, and lower cost. And we were working on liquid crystals because they can visualize ultrasound. And we were exploring one thing. And let me show you something first. I have warm hands. I'm wondering whether you know what that is. So this is, well, that's my hand. This is the thermal image of my hand. And this piece of plastic is thermochromic liquid crystal sheet. Thermochromic because it changes color with temperature. We use these films on transducers to visualize ultrasound. Let's see whether that works. This is the same mode. This is 11-0 mode, but now it looks a bit different to the vibrometry picture. And that's because it only gives you maximum displacement. It will not give you phase. It will just give you areas that move up and down. What is happening here, we are absorbing energy, converting it to thermal and visualizing that. But we do it with sufficiently high resolution, we can see the detail. And let's look at other nice images that we have taken, because now we can go through the whole frequency range really quickly. It takes about a couple of seconds to acquire one image. That's 740, that's 2 something megahertz, that's 8 megahertz. Sorry, I couldn't resist this one. And you can look at them all together. So we think it's not going to give you the same information as vibrometry. It will not give you frequency, it will not give you phase, but it is a visual method. It's compatible with the existing robotic inspection. If you remember at the beginning of the talk, I mentioned that company which already has solved the problem of putting cameras on a robot and using artificial intelligence to analyze the input. So this is an interesting method for either permanent installation or maybe removable sensors. But let's also see what we can do with that data. Before I move on to that, this is a real-time video of us switching between, switching on vibration. It's 120 kilohertz. It's on, it's on, it's off. Now switching on 6.7 megahertz. It's off. Switching on 620 kilohertz. So it can, it shows you in real time how the sensor works. It's quite responsive. It's versatile, and it's visual. The interesting thing is that you only need out-of-place displacement between 1 and maybe 10 nanometers in the frequency range that we covered to be visible. That's a really small displacement, and we can visualize it already. So yes, what can we do with this data? We can extract whole temperature maps from the color, from the hue, and from the temperature change. We can relate that to interferometry figures, and that aligns well, and we can start making conclusions about the displacement amplitude. It's good for visualizing patterns, and if you know which pattern to expect, or if you want to link that to properties of, for example, cracks, having positive interference next to the crack opening, if you are sending waves, maybe you can visualize increase in energy next to the crack opening. All things are possible. I was talking about higher frequencies, 300 kilohertz and up, but what happens at lower frequencies? And they're harder. They're harder because if you think about the wavelength of sound, ultrasound, that you need to absorb, it's okay-ish at 10 megahertz. This film is not very thick. It's just a plastic film. It's very difficult for it to absorb acoustic wavelength of 37 millimeters. But we were able to add a bit of special backing layer and absorb that. So this is the image of the tip of the ultrasonic horn. It's not just thermal. This bright point in the middle disappears when you switch the ultrasound off, but it appears immediately when you switch it back on. So we know this is due to ultrasound. What else can we do with this at 40 kilohertz? Well, we can set up standing waves. This is a standing wave pattern on plexiglass plate. This has been processed for hue so that we can see a little bit better. The type of wave here is A0 lamp wave, if you're interested. And it's on a highly dispersive edge of it. This is why the wavelength is so small. We can actually still be in the right region to set up the standing wave pattern. Right, we can look at standing wave patterns in plates. What else can we do? Well, of course, acoustic metamaterials are really, really attractive to look at. Can we see energy distribution in an acoustic metamaterial? So this plate is technically an acoustic metamaterial for certain frequency range, and it works at 40 kilohertz. The wavelength of the ultrasound at 40 kilohertz is fairly similar to the gap between the holes. And if we put our probe, so first of all, we see the distribution of ultrasound. It behaves differently inside the holes. We get evanescent wave seeping into the sensor, being absorbed, making the holes brighter. It's not thermal, we've checked that. And if you place your ultrasound generation tip in different places, you get different distribution. What we can extract from that is we can then process the data. This is work by our PhD student, Martha, and she produced these beautiful maps. Now we are working on linking this with modeling, where we can start understanding what we are seeing in experiment and how that relates to model of ultrasound propagation in acoustic metamaterial. So let's summarize, I think, in good timing. We talked about EMATs, electromagnetic acoustic transducers. They're versatile. We have miniaturized them for robotic inspections, and they actually work. Magnetostrictive patch transducers, they're very effective. They're really versatile. They have huge potential, and not only on deployment for pipes or inspection of under supports. They don't have to go on a conductive material. They can go on concrete pillars, for example. This is the photo of a sensor being attached to a concrete prism. And the third topic we covered today is using liquid crystals. Here it's a thermochromic liquid crystal for visualizing acoustic fields. These can be passive and low-cost sensors, and this is a pretty large area, and this is not very expensive. It will not give you the information that vibrometry will give you, but it gives an interesting insight into things, and it, I think, is particularly interesting for visualizing acoustic metamaterials and plates. So with that, I wanted to thank our funding bodies, RC&D and EPSRC. I want to thank my colleagues, and I hope I haven't omitted anyone, but so many people I have worked with who helped me, that it's great to work in a nice community, and I thank you for attention. Thanks a lot. I will be very happy to answer any questions. Right, I'm not sure I can see anything in terms of there are no open questions. And I can't see participants.
Hi, Arkanza. Thank you very, very much for your fabulous presentation today. It's been fascinating, and we very much appreciate you coming on and running the webinar for UCAN. If anybody has got any questions before you log off, that you can just drop them into the Q&A, and Arkanza can see them written in there. Other than that, we thank you very much for your attendance today. And this webinar, as with all UCAN webinars, will be put on our YouTube channel. So if anybody's interested in seeing any of the backlog catalogue, then please feel free to check out that. It does look like you've got one question in there now, Arkanza, if you can see that.
Yes, absolutely. Could I ask if the magnetostrictive sensor was sensitive to electromagnetic noise? Yes. they would be sensitive to electromagnetic noise. You have to be careful about keeping your grounded on the detection side of things. They are as sensitive as EMATs. They're just cause of why they will pick up noise. You need to take, you can insulate things. You can protect things. Obviously, we don't do that in the lab, so you go into a different room and it looks a bit different. But this is something that is solved and is solvable generally. Any more questions? The magnetostrictive sensor actually was also sensitive to any external field. So if you are running it at low bias field and come in with a magnet and wave it next to the sensor, that also doesn't go down very well. So if you are using something where you have really high magnetic fields fluctuating, then you probably don't want to use that. There are other methods you can use.
Well, once again, thanks very much for your fab webinar for us today. We appreciate you coming along. Thank you very much, Okanza, and I think that's wrapped that up nicely. Thank you very much for your time.
Thank you, Jane.
Thank you.
Thanks a lot. Cheers.